right. Hello, class. Good morning. Looks like no one is watching right now. That's all right. Hopefully, you'll tune in later today um, and check out this lesson. So, a couple of announcements. Go ahead and fill out the May 8th homework when you get the chance. And you could also even submit your quiz for next week early. So your quiz for next week is going to be just the daily items from this week. Okay, so you can submit that now if you. I will send out a remind, and I'll be on Discord Sunday afternoon. If you have any questions at all about the AP exam, we can try to figure it out together. There's going to be no class Monday, Tuesday, Wednesday of next week, and that is because of the AP exam. So we'll just take a break. It's time for a break. We've been reviewing for 3 weeks now, so it's time to take a break. Yeah, so I think that's all my announcements. So I'm going to go ahead and I see one concurrent viewer. I wonder if that's my mom. Mom, if that's you, text me. I'm curious if you're my concurrent viewer. Because I'm guessing most of the students are asleep still. All right, so yesterday I decided to do a practice, do the released sample questions for the 2020 AP exam. Today I'm going to go back to my original plan for yesterday, which was to do the 2013 mechanics free response. So that's what I'll be working on today. So let's take a look at it. Student places a 0.4 kilogram glider on an air track of negligible friction and holds it so that it touches an uncompressed ideal spring as shown in figure 1 above. The student then pushes the glider back to compress the spring by 0.25 meters as shown in figure 2. At time t equals 0, the student releases the glider and a motion sensor begins recording the velocity of the reflector at the front of the glider as a function of time. The data points are shown in the table below. At time t equals 0.79 seconds, the glider loses contact with the spring. Okay. On the axes below, plot the data points for velocity as a function of time and draw a smooth curve that best fits the data. Be sure to have an appropriate scale on the vertical axis. So we can see that the maximum velocity is about 0.5 meters per second. So I will make this to be 0.5. 0.5. So that's 0.5 right there. So our first data point is 0, 0. Our second data point is 0.25, 0.25, so that would be right here. Our third data point is 0.5, 0.43. That's maybe right here. Then we have 0.75, 0.48. Right here roughly. And then we have 1, 1.5, and 2 are all at around. So it looks something like this. Okay. I'm going to draw a smooth curve that best matches the data. So something kind of like this. Play around with that to try and make it better matching. Something like that. The student wishes to use the data to plot the position x as a function of time for the glider. Explicitly label any intercepts, asymptotes, maxima, or minima with the numerical values or algebraic expressions as appropriate. Okay. So what we can see is basically the velocity is constant after time 1. So after time 1, we've got a straight line for the position time graph. So after time 1, it looks like this. Oh, it didn't even ask me to draw it yet. So let me explain what I'm going to do. Basically, what you would want to do is integrate. So you do the area under the curve of the VT graph. That gives us displacement. Okay. So now I'm going to sketch the position as a function of time, and so it's going to look like a straight line after 1 second because the velocity is constant. So that means the slope of a position time graph is constant. In the beginning, we have acceleration though, and the acceleration decreases to 0. So we're going to have something that kind of looks like this. It accelerates to reach its maximum velocity, and then after that, it has a constant velocity. And then the slope of this part would be roughly 0.5 meters per second. Okay. So we did part 2. Part C says calculate the time at which the glider makes contact with the bumper at the far right. So we can see that after 1 second, well, at t equals 0.79 seconds, the glider loses contact with the spring. So what I would say is at t equals 0.79 seconds, we can also say that the position is 0.25. Why do I say that? Because it says that the spring is compressed by 0.25 meters. So that means that once the spring gets back to 0.25 meters, we've lost contact with the spring. Okay, so that means in order to, so basically we're going to have delta x equals v naught t, because there's no acceleration after that time. And we can see that at 0.25 meters, we would have an additional 1.75 meters to go in order to hit the bumper, because the whole track is 2 meters long. And the velocity we know is 0.5. So we can solve for time, and that tells us that the time is 3.5 seconds. This is the time after losing contact with the spring. So we have to add the 0.79 seconds to that to get roughly a time of 4.3 seconds or so. All right. D, calculate the force constant of the spring. So one of the things we notice here is that basically for the first 0.79 seconds, we have simple harmonic motion. All right? And in fact, it's easy to see that we're going to get essentially a quarter of a period, because a full period would be, a full period of simple harmonic motion would be also the down and then the below, like this. So what that means is that a full period is 4 times 0.79 seconds. Okay, so that would be 3.16 seconds. All right, and that equals 2 pi square root of m over k. The mass is, I think it tells us the mass, 0.4 kilograms. So we can take this and solve for k, which I will do. And I got about 1.6 newtons per meter. So that's a very flabby, not a very strong spring at all. Oh, James is the only one. Okay, I just noticed that. Just took a look at the live chat. How long is it going to take you to abandon this? I bet you won't make it through the whole lesson. Let's see. That's pretty funny, though. E says, the experiment is run again, but this time the glider is attached to the spring rather than simply being pushed against it. Determine the amplitude of this simple harmonic motion. Well, that's pretty easy. That would be 0.25 meters, because it's that's how far the spring is pushed back. Calculate the period of the resulting oscillation. I literally just did that. It was 4 times 0.79, 3.16 seconds. So there you go. Question 2. A box of mass m is initially at rest and is acted upon by a constant applied force of magnitude F sub a, as shown in the figure above. The friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude kV, where v is the speed of the box and k is a positive constant. Draw the forces that act on the box. We've got the applied force. We've got the drag force. I'm going to draw the drag force as being smaller than the applied force because it hasn't reached terminal velocity yet. We've got the normal force. And we've got the weight force. We got 4 forces. So that is A. B says write but do not solve the differential equation that could be used to determine the speed via the box as a function of time. So we have F equals ma, net force equals ma. And so we have, and the net force is going to be the applied force minus kV, and that equals m dv dt. All right. Hey James, we had a staff meeting this morning, and I've been doing this. You might get a kick out of this. I've been doing this thing where before the staff meeting, I always log in and I display the video, and then I do something obnoxious. So last time, for the last staff meeting, I ate a banana like really obnoxiously, like I was like, and then this time I ate tortilla chips, so the bag was crinkling the whole time, and then I gargled mouthwash. So, and then I got muted, so I got blocked from the Zoom meeting, but it was worth it. I think next time my idea is to get a drink with ice in it and have just a little bit of liquid left and just slurp the liquid. Okay. Determine the magnitude of the terminal velocity of the box. Acceleration equals 0 at terminal velocity. So we have basically F sub A equals K times V, which says that the terminal velocity is F sub A over K. D, use the differential equation to derive the equation for the speed of the box as a function of time. So once again, I want to separate variables. So I have dt equals m dv divided by f sub a minus kv. I'm going to take both sides and multiply by k and divide by m. And so that gives me k over m dt equals dv over f sub a over k minus v. Then I integrate both sides. On the right-hand side, I will be integrating from 0 to v. On the left-hand side, I'll be integrating from 0 to t. So that gives me, maybe I better turn my lamp on. It's a little bit overexposed. So I have k over m times t equals natural log of, actually minus natural log of f sub k, f over k minus v plus natural log of f sub a over k. So that gives, so we just solve it. We've done this a lot of times by now. I suppose I'll solve it. Minus k over m times t equals natural log of 1 minus kv over f sub a, e to the minus kt over m equals 1 minus k over f sub a times v. So that gives v of t equals f sub a over k times 1 minus e to the negative kt over m. There's your answer. So that just comes from algebra, solving the differential equation. So, part E says, on the axes below, sketch a graph of the speed of the box as a function of time. Explicitly label any intercepts, asymptotes, maxima, or minima. It's just going to look like it's going to go up, and then it's going to reach that terminal velocity. Okay? All right. Question 3. Ooh, this looks kind of interesting. A disk of mass m and radius r is supported by a rope of negligible mass as shown above. The rope is attached to the ceiling at one end and passes under the disc. The other end of the rope is pulled upward with a force F sub A. Calculate the magnitude of the force necessary to hold the disc at rest. So what I would want to do is notice that from a free body diagram, the disc has the tension going up and the tension going up twice. Okay? So F sub A and F sub A. So that means that the net force is 2 F sub A minus mg. And if it's being held at rest, then that means the net force is equal to 0. So F sub A is mg over 2. All right. At time t equals 0, the force is increased to 12 newtons, causing the disc to accelerate upward. The rope does not slip on the disc as the disc rotates. Ooh, this is going to be a little bit tricky. Calculate the linear acceleration of the disc. Okay. Calculate the angular speed of the disc at t equals 3 seconds. All right, so this one is a little bit tricky because we're going to have, when you have a rope that is pulling something and it's causing the thing to rotate, we actually have two different tensions. Okay, so we're going to have a tension on the left, and we're going to have a tension on the right, which is just F sub A. And they're not going to be equal to each other. So we're going to have to use net torque equals I alpha. Okay. All right. And so what is the net torque? It's F sub A times R minus T sub L times R. And that equals I alpha. Then we have a Newton's second law, a linear form of Newton's second law, which is going to be just F sub A plus T sub L, the tension on the left, minus mg equals ma. All right? So we have these two equations. The unknowns are the tension in the left, the angular acceleration, and the linear acceleration. So we have three unknowns. So we're going to need one more. We're going to need one more equation that expresses the geometry of the situation. So the geometry for this one is a little bit tricky. I think we're still going to have, if it does one full revolution, then that means it climbed upward by 1. So, or by 2 pi r. So we're still going to have alpha times r equals the acceleration. Okay? So this comes from geometry. So plugging that in, we get F sub A times r minus T sub L times r equals mr squared over 2. And then, so I plugged in the expression for inertia. And then I can also plug in the expression for alpha. Alpha equals A over R. Okay. So this cancels that. that cancels that. So we have f sub a minus t sub l equals ma over 2. Then we also have this equation, which is f sub a plus t sub l minus mg equals ma. So I'm going to add these two equations. 2f sub a minus mg equals 3/2 ma. That says that the acceleration equals, well, let me just plug in the numbers. 2 times f sub a is going to equal 24. mg is 20. And then that equals 3/2 times 2 times a. So we have 4 equals 3a, which says that a is 1.3 meters per second squared. Okay, that was kind of a long one. C, calculate the angular speed of the disk at 3 seconds. So we know that alpha is going to be equal to a over r. So it's going to be 1.3 over 0.1, or 13 radians per second squared. Okay, so then I have omega final equals omega initial plus alpha t. Omega initial is 0. So we have 13 times 3 seconds. It should be roughly 39 radians per second. D says calculate the increase in total mechanical energy of the disk from 0 to 3 seconds. Okay, so we have a basically our final mechanical energy. Our initial mechanical energy is 0. Our final mechanical energy is the rolling kinetic energy plus the translational kinetic energy. So that is k tot plus mgy. So I'm not really inclined to plug in the numbers. It's just going to take a lot of time. So I'm just going to leave it at that. And then E says the disk is replaced by a hoop of the same mass and radius. Indicate whether the linear acceleration of the hoop is greater than, less than, or the same as the linear acceleration of the disk. A hoop's inertia is mr squared. Okay? So that is greater than the inertia of the disk. So that means that if it has a greater inertia, it's going to rotate more slowly, so I would say that it will be less than. I think that's the end of the exam. Cool. So thank you for the entertainment, James, and thank you to the 3 of you who watched. I'll send out a remind on Sunday for our question and answer session on Discord for Sunday. Also, if you check the Discord, I had the chance to post what the units are that are going to be on the AP exam, so some of you are asking questions about that, so please check it out. All right, thanks for watching. Have a good day.